Continuing now with the Miller handout, the main point of the next box is that the chlorine species, when it fragments, costs a certain amount of energy. This is a relatively weak bond. 59 kcals per mole is not that strong compared to, say, 100 kcals per mole for a carbon-hydrogen bond or 80 kcals per mole for a carbon-chlorine bond. So it's a relatively weak bond, but it still costs 59 kcals per mole of energy to break a chlorine-chlorine bond. By contrast, of course, breaking a bromine-bromine bond is slightly easier, but it still costs a significant amount of energy. 46 kcals per mole. But once you have formed these radicals, then the relatively important things to keep in track of are the energies associated here. So this initiation step costs energy, but in the end it won't necessarily matter. What does matter though is the energies involved in the propagation steps. So the chlorine abstracting a hydrogen costs 105 for a carbon-hydrogen bond of this type, which is to say a methyl, but you get back 103 kcals per mole for making a chlorine-hydrogen bond. So on net, that's not bad. That's relatively minor change in energy there. But what you also are doing, of course, in the second step is breaking a chlorine-chlorine bond and then making a carbon-chlorine bond. And overall, this gains a fair bit of energy. At the cost of a relatively weak chlorine-chlorine bond, you get out a fair bit more energy back from making the carbon-chlorine bond. Again, negative energies here are actually a good thing. So if you go down minus 25 kcals, then overall the process is quite exothermic. This is generating heat and this is downhill to the tune of 23 kcals per mole. So this is a relatively unselective reaction because, hey, you can go ahead and generate a fair amount of energy along the way and it's going to be reasonably insensitive to the strength of this bond. However, when you are looking at the bromine process, then the strength of the bond involved, the carbon-hydrogen bond, isn't any different. It's still 105, but you get out a whole lot less energy. The bromine-hydrogen bond isn't anywhere near as strong. So that costs you 17 kcals per mole. Meanwhile, when you are breaking the bromine-bromine bond, that's now easier. It's 46 instead of 59, but again, the energy you get out on the far side isn't as good. So this only gets you back 26 kcals per mole, and it costs you 17 in the first place. So the net of the two steps is minus 9, which is to say it is slightly exothermic, but not dramatically so, whereas the chlorine is much more indiscriminate. You can imagine that this is going to be quite sensitive to the differences in energy of the specific carbon-hydrogen bonds being abstracted. So his example here illustrates it only for methyl, whereas a more detailed table of energies will illustrate the problem for a primary, secondary, or tertiary system. This page from the Bruice textbook, I think, really does a nice job of illustrating the major source of the selectivity. So a chloride plus a primary alkane will lead to a very slight energy difference, but you actually get 2 kcals per mole back out of this first initial propagation step. And when you have a secondary system, you get a little bit more energy out, 4 kcals per mole instead of 2. And when you have a tertiary, you get even more energy out, 6 kcals per mole instead of 2. So these are all slightly favorable initial step of having the chloride abstract the proton. By contrast, when the bromine is doing the abstraction, all of these steps cost energy. It's upwards in energy. And so the reaction is going to be much more sensitive to the difference in energy overall. Again, the spread here isn't very large. It's only 4 kcals per mole, which is the same as above. But the difference is it costs you energy to abstract the proton and make the HBr bond and create the primary radical. It costs you 14 kcals per mole to create the primary. It costs you 12 kcals per mole to create the secondary. It costs you only 10 kcals per mole to create the tertiary. Again, the Bruice textbook has an image here that I think does a better job of explaining things than the corresponding Miller image. And the idea is that when alkanes react with radical to create the HCl and the alkane radical, this is an exothermic reaction overall. The energy differences are small. This is only 2 kcals per mole lower than you started with and 6 kcals per mole in the best case. But these roughly 2 kcal per mole jump between primary, secondary, and tertiary will have a flattening effect up at the transition state. There's a relatively small difference in energy at the transition state, and that's the part that matters. The reaction is going to be almost insensitive to these differences in energy here because they're relatively small. But since the reaction of an alkane with Br dot to form HBr and the alkane dot is endothermic, it's uphill, it costs you energy, then these energy differences are going to be almost as large as the energy differences between the products themselves. So there's almost a 1.5 kcal difference in activation energy here, even though the difference in energy is the same in the products. And that's simply because this is uphill in energy, whereas the chloride was downhill in energy. Again, for this first deprotonation step, the one that creates creates the radical that eventually gets filled, there's going to be a significant difference in energy of the activation energy. So you're going to end up making quite a bit more of the tertiary product because this will be nearly 3 kcals per mole, give or take, lower in energy than, say, the primary. This is the energy difference that matters, the energy of the transition state, and you end up making a lot more of the tertiary system. Really, if you're going uphill, the reaction is going to be much more sensitive to small differences in energy, whereas if you're getting energy out, the reaction isn't necessarily going to care as much. This paragraph at the bottom of the Bruice handout really is the best way of illustrating the difference here, and they talk about the Hammond postulate, but the Hammond postulate basically says that a transition state is going to resemble whatever it's closest to in energy. If you are close in energy to the reactants, then the transition state will closely resemble the reactants. But if you're closer in energy to the products, then the transition state will more closely resemble the products. And that's really what Miller is trying to show with this particular box. Since the bromine reaction is further along at the transition state, then there's going to be more radical character in the transition state. It's going to more closely resemble what it actually ends up looking like, which is the radical. But again, the upshot is it's just more sensitive to the energy differences because the transition state closely resembles the products here, whereas over here, on the chloride side, the transition state closely resembles the reactants. And the reactants are all about the same. Some unreacted alkanes, so there's not a whole lot of difference there. Differences get minimized in the chlorine case. They get magnified in the bromine case. And the final thing I want to draw your attention to in the Bruice handout is these relatively small but significant energies for bond dissociation. A methyl CH bond of a methyl is about 105 kcals per mole, whereas a generic primary is down to 101 kcals per mole. It's 99 kcals per mole for a secondary and 97 kcals per mole for a tertiary. These subtle energy differences here that the bromination radical mechanism is capable of distinguishing among. These subtle 2 kcal per mole differences are enough to give rise to the massive selectivity differences that you see. Again, as long as what you're looking at is relatively small energy differences, they could still have a huge effect in the distribution of products, changing from a roughly indiscriminate reaction with chloride, which is insensitive to these energy differences, to extremely selective, 90+% for the tertiary with the bromine case, because it is sensitive to these relatively small energy differences. These energy numbers come from that table, but they explain basically all of what you're seeing. Bromine reactions are selective, you will make the tertiary products. Chlorine reactions are indiscriminate, you'll make a little bit of everything. In other words, chlorine reactions are not particularly synthetically useful.